Okay, everyone, this is 3.5, part 2. We are now going to go over some derivatives of the inverse trigonometric functions. Um, what you need to know is this. So on the left are the derivatives, and on the right are the domains for these functions. But I'm going to show you where one of them comes from, if you're interested. So we have y equals sine inverse of x. That means x equals sine of y. So we have x equals sine of y, and we take the derivative of both sides. On the left, we have 1, and on the right, we have cosine of y times the derivative of the inside by the chain rule, which is y prime. Now we get y prime by itself by dividing both sides by cosine. So y prime equals 1 over cosine of y. So now we multiply both sides by sorry about that. I think I misspoke. Let's pick it up right here real quick. So we have y prime equals 1 over cosine. Now this is kind of just a note that because 1 equals sine squared plus cosine squared, let's get cosine squared by itself. So now if I take the square root of both sides, we get this. So now cosine is equal to 1 minus sine squared. So now that we're just going to plug that into the bottom. So we get 1 over 1 minus sine squared, and sine was x, so that's where we get the x squared. So at the end of the day, this is my derivative of arcsine, which is the same thing as this notation. So that's where the derivative comes from. You'll notice that they're all pretty similar. So for sine, we have 1 over square root of 1 minus x squared. Cosine is the same except negative. Tangent is a little bit different. And tangent here is definitely the most important one because you're going to use this tool a lot in Calc 2. Tangent inverse derivative is very important. Okay, so here's a little reminder. We have a function that takes an angle measure in and spits out the distance above the horizontal diameter. That is my sine. We restrict the domain of sine to go from negative pi halves to pi halves, including both of those numbers. And the max and min values of sine are negative 1 and 1, and we get every number in between. So now we're saying, okay, consider this function arcsine of x squared minus 1. Find the domain of f. So we have arcsine of x squared minus 1. This thing right here is called the argument of a function. Which is different than this, which is the input, because we're dealing with a composition of functions. X is not what goes into arcsine. X goes into this function, which is x squared minus 1, and then that is what goes into the arcsine function. And that's how we get arcsine of x squared minus 1. Okay? So what we know about the argument here is that it has to be between negative 1 and 1, because that's the domain of arcsine. So I know that since the domain of arcsine is this, then this guy must be within that same range. Now all we have to do is get x by itself. We're going to add add 1 to both sides. And we take the square root of both sides. And so when we take the square root of both sides, plus we have this kind of like compound inequality, things are going to get a little bit dicey, but let's just extract this part. So we have x squared is equal to 2. So here we know clearly that x is plus or minus square root of 2. So we definitely have plus or minus square root of 2 as numbers to consider. So here's 0, here's square root of 2, here's negative square root of 2. And we know that both of these numbers will work. And you can think about it as breaking this into 3 regions. We have the left, the middle, and the right. You can check numbers in the middle to see if they will work. But basically, it's this less than, right? That is, we're thinking of the numbers, that are not further away, right? Like not over here and not over here. And you can check it with the graph, but basically it's these numbers here in the middle that will make this work, right? I mean, you can check, right? Like let's say 1 is over here. So is this true? So 0 is indeed less than or equal to 1 and is indeed less than or equal to 2, right? So that's a way to check. And you can do the same check for negative 1, right? Look, here's negative 1. So anyway, our domain here is going to be from negative 2, negative square root of 2 to square root of 2. Now we want the derivative. So that was number 1. Let's maybe partition that off. Let's look at problem 2, the derivative. So the derivative of sine inverse is 1 over 1 minus x squared in square root. There we go. Okay, so the derivative of this guy, inverse sine of x squared minus 1, is 1 over square root of 1 minus the inside function squared multiplied by the derivative of the inside function. So we have the first thing squared minus 2 times x squared times 1 plus the last thing squared. Let's just check that. So we have x squared squared. Oh, I need to put that in parentheses. X squared squared, check, minus 2 times x squared times 1, check, plus 1 squared. Okay. So we've got negative x to the 4th plus 2x squared this 1 is going to cancel over here with that minus 1, so we get negative x squared plus 2x squared. So I'm going to pull out this x squared over here, and we're left with negative x squared plus 2. So we could write that like this. X squared times 2 minus x squared. Something like this is our derivative. And then we're being asked to find the domain of f prime. So this is f prime. The domain. So when we have a radical, the thing on the inside, the radicand, must be non-negative, must be greater than or equal to 0. But if we are dividing by a radical, then the radicand must be strictly positive, because yes, we cannot take the square root of a negative. Over here, taking the square root of 0 is fine, because the square root of 0 is 0. But then if we divide by 0, then that's not okay. So that what is inside the radical symbol must be positive. So what we can do is take this and first we can just set this equal to 0. So then this guy gives me x is 0, and this one tells me that x is plus or minus square root of 2. So we can do the same thing as before. We have 0, root 2, negative root 2. And then we can just check in each of these intervals where the function will be positive. So one way to do that kind of quickly, right? We have negative x squared times x squared minus 2. And let's just, is that the same thing that we got? X squared times, yeah, we just had the negative pulled out. So what we have is the same. So anyway, where is this guy positive? Well, from negative root 2 to root 2, it's not positive here, where we're getting 0 out, right? Because if I put 0 into here, then this whole thing will become 0. So it looks like we want, all of these and all of those. So from here to there to there. So we can say from negative root 2 to 0, union 0 to root 2. And this is my part 3. Simplify cosine of tangent inverse of x. Okay, this is an angle measure, so that means tangent inverse of x is an angle measure. I can say that tangent of that angle is x. We're going to do the right triangle trick. There's my angle. Tangent is opposite over adjacent. So then the Pythagorean theorem tells me that 1 squared plus x squared is the hypotenuse squared. So the hypotenuse is going to be, and I can just take the positive one. So now I want cosine of theta. Cosine of theta is adjacent over hypotenuse. So this means cosine of theta is the adjacent 1 over the hypotenuse, 1 plus x squared. These are some facts about the arctangent or the inverse tangent function. The domain is from negative infinity to infinity. How does that make sense with this picture? Well, because the tangent is the slope of the terminal ray. So as we rotate around the circle, we will get every positive and every negative slope, right? Like down here, we're going to get all the negative slopes. Up here, we're going to get all the positive slopes. The range is from negative pi halves to pi halves. So let's look at this one, this circled right here. So if tangent inverse of x is pi halves, then that means tangent of pi halves is x. But tangent of pi halves doesn't exist. However, as theta approaches pi halves, so we can simulate that with my ray getting closer and closer to pi halves, the tangent blows up, right? The slope gets increasingly positive. The slope increases without bound. So we can use that way of thinking over here in this example. So calculate the limit as x approaches 2 from the right of the arctangent of 1 over x minus 2. So with these problems, we can take it layer by layer. Let's think just about x minus 2. As x approaches 2 from the right, that means from values of 2 that are bigger than 2, we can think about 3, then 2.5, then 2.4, then 2.3, then 2 point blah, 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 right? Getting closer and closer to 2 from above. As x approaches 2 from above, x minus 2 gets closer to 0 and is positive because this number here is going to be bigger than 2. Okay, thus 1 over x minus 2 approaches infinity because I'm dividing by something that's getting tiny, 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 but positive. So this thing gets closer to infinity. We know that arctangent of 1 over x minus 2 is an angle measure. So that means I'm just going to rewrite this, right? This is the inverse notation. I'm going to use the forward function notation using this kind of schematic here in my mind. Tangent of theta is 1 over x minus 2. So which theta corresponds with tangent approaching positive infinity? Well, we've already talked about that before. Pi halves. Pi halves. So these are the other trig functions. We call these the reciprocal trig functions, right? Like cosecant of x is the reciprocal of sine. Secant of x is the reciprocal of cosine. Cotangent of x is the reciprocal of the tangent. And these are the inverses, right? So this is inverse cosecant, inverse secant, inverse cotangent. And here are their derivatives. Just add these to the bag of derivatives that you're memorizing. Thank you all for your patience with this long lesson.